September 16, 1943. Bougainville in the Solomon Islands. First Lieutenant Kenneth Walsh completed his mission debrief, recording observations that would prove historically significant for Pacific air warfare development. Walsh had just returned from a bomber escort mission flying the Vought F4U Corsair, and his notes documented a critical problem facing American fighter aviation. The new aircraft provided substantial advantages in speed and firepower compared to Japanese fighters, particularly the Mitsubishi A6M-0. However, achieving hits against maneuvering enemy aircraft remained extraordinarily difficult, even for experienced pilots. The fundamental challenge was deflection shooting, firing at a moving target while both aircraft executed high-speed maneuvers, requiring instantaneous mathematical calculations that human pilots struggled to perform accurately. What Walsh and thousands of other Marine and Navy aviators operating in the Pacific could not know in September 1943 was that British engineers had already developed a solution. A device incorporating precision gyroscopes and optical computing elements would soon transform aerial gunnery from a skill requiring years of practice into a capability that could be taught in weeks. The Mark 18 Gyroscopic Gunsight would reach Pacific theater squadrons within 12 months, fundamentally changing the mathematics of air-to-air combat. If you appreciate detailed, evidence-based World War II history told through primary sources and operational records, please like this video and subscribe to the channel. Leave a comment letting us know where you're watching from. The Vought F4U Corsair had entered Marine Corps combat operations in February 1943, bringing unprecedented performance capabilities to American fighter aviation in the Pacific. The aircraft was powered by the Pratt & Whitney R2800 double Wasp radial engine, which produced over 2,000 horsepower and enabled the Corsair to exceed 400 miles per hour in level flight. This made it the first American single-engine fighter to break the 400 mph threshold. The aircraft's armament consisted of 6 Browning M2 heavy machine guns, each chambered for 50 caliber ammunition and firing at approximately 800 rounds per minute. When these weapons were accurately aimed, they delivered devastating firepower, capable of destroying enemy aircraft with short bursts. The fundamental problem was achieving accurate aim. Deflection shooting, the technique of hitting a moving target from a moving platform, represented the single most challenging aspect of aerial combat throughout World War II. When a Corsair traveling at 400 mph attempted to engage a Zero executing evasive maneuvers at 300 mph, the pilot could not simply aim directly at the target. Instead, he had to aim at a point in space where the target would be when the bullets arrived. The 50 caliber bullets left the guns at approximately 2,700 feet per second, but even at this velocity, they required measurable time to reach distant targets. At a range of 500 yards, the bullet flight time approached half a second. During that interval, a Zero in a standard rate turn would travel nearly 200 feet. The pilot had to lead the target by precisely that amount, continuously adjusting as ranges and angles changed throughout the engagement. This calculation had to be performed while pulling G-forces that constricted vision and made complex mental arithmetic impossible. The standard gun sight installed in Corsairs through 1943 and into early 1944 was the Mark 8 reflector sight. This device offered no computational assistance with deflection shooting. It consisted of an illuminated reticle projected onto a glass plate mounted in front of the pilot's line of sight. The reticle showed where the guns were pointed, nothing more. The pilot had to estimate lead angle entirely through experience and intuition. Talented pilots developed an instinct for deflection shooting after months of practice and combat experience. These pilots learned to anticipate target movement, to sense the proper lead angle required for various engagement geometries, and to fire at the precise moment when instinct and geometry aligned. Many pilots never developed this instinct at all. Combat records from 1943 show that numerous pilots expended all their ammunition without achieving a single kill, their bullets consistently passing behind fleeing targets because their mental calculations were fractions of a second too slow or their lead angles were a few degrees too shallow. Lieutenant Kenneth Walsh, flying with Marine Fighting Squadron VMF 124, represented the exceptional pilots who had mastered deflection shooting through natural ability and extensive practice. On May 13, 1943, Walsh became the first Corsair pilot to achieve ace status by shooting down 3 Japanese aircraft in a single mission, bringing his confirmed total to 6 victories. Walsh had learned through hundreds of practice hours to anticipate target movement and to sense correct lead angles. His success came from innate understanding of 3-dimensional motion combined with exceptional hand-eye coordination. Most pilots lacked Walsh's gifts. According to Marine Corps training records, the average fighter pilot arrived in the combat zone with approximately 200 hours of total flight time. Of those 200 hours, perhaps 20 involved gunnery practice, typically against towed sleeve targets that flew straight and level. Against maneuvering Japanese fighters flown by experienced combat pilots, these average American pilots struggled to achieve hits. Operational reports from 1943 document numerous instances where pilots engaged enemy aircraft, expended all their ammunition, and returned to base with no confirmed kills. Their bullets had passed harmlessly behind or below their targets because the mental calculations required for accurate deflection were performed too slowly or incorrectly under the stress of combat. The British had recognized the deflection shooting problem early in the war. In 1941, the British Ferranti Company began production of the Mark II gyro-gunsight, a revolutionary device that employed spinning gyroscopes to automatically calculate deflection angles. The operating principle was elegantly straightforward. Gyroscopes resist changes in orientation due to conservation of angular momentum. When an aircraft executes a turn, the gyroscopes inside the gun sight remain pointed in their original direction, while the aircraft structure rotates around them. By measuring this resistance through precision gears and optical elements, the sight calculates the aircraft's rate of turn. That rate of turn directly corresponds to the lead angle required to hit a target at a given range. The sight automatically adjusts the aiming reticle to compensate, moving it ahead of the target by precisely the correct amount. Royal Air Force pilots using the Mark II gyro-gunsight reported substantial improvements in combat effectiveness. Spitfire pilots, who had previously struggled with deflection shooting, found themselves achieving hits on their first firing pass. The sight eliminated the need for complex mental calculations, allowing pilots to concentrate on tactical positioning and situational awareness rather than geometric computation. United States military observers recognized the technology's potential immediately. The U.S. Army Air Forces contracted with Sperry Gyroscope Company to produce American versions of the British design. The Army Air Forces designated their version the K-14, while the U.S. Navy and Marine Corps designated theirs the Mark 18. Both were functionally identical to the British Mark II, with minor modifications for American manufacturing processes and cockpit integration requirements. Sperry Gyroscope Company's facility in Lake Success, New York, employed over 20,000 workers at peak wartime production. The facility manufactured gyroscopic gunsights alongside bomb sights, fire control systems, and navigational equipment for all branches of the American military. The Mark 18 was substantially larger and more complex than the reflector sight it replaced. Where the Mark 8 reflector sight was a compact unit weighing approximately 5 pounds, the complete Mark 18 system weighed 12 pounds and required significant cockpit modifications for installation. Sperry engineers explained that the additional weight was unavoidable. Inside the housing were 2 independent gyroscopes measuring pitch and yaw, spinning continuously once electrical power was applied. These gyroscopes contained the mechanical solution to deflection shooting, the single most difficult aspect of aerial gunnery that had challenged fighter pilots since World War I. The Mark 18 design incorporated lessons learned from British Royal Air Force combat experience. The sight presented 2 independent reticles visible to the pilot through the optical glass. On the left side, a fixed cross indicated where the guns were actually aimed, providing a reference for the aircraft's bore axis. On the right side, a gyro-stabilized reticle consisting of a center circle surrounded by 6 diamond-shaped pips showed the computed aiming point. As the pilot maneuvered to track an enemy aircraft, the gyroscopic reticle automatically positioned itself ahead of the target by exactly the correct lead angle for the current turn rate. Operating procedure was simplified compared to reflector sight techniques. First, the pilot set the target's wingspan using a control dial on the sight itself, selecting from known values for Japanese aircraft types. The A6M0, the most common opponent in the Pacific, had a wingspan of 36 feet for standard variants. With wingspan selected, the pilot adjusted a twist grip integrated into the throttle control to expand or contract the diamond-shaped ranging reticle until it matched the apparent wingspan of the target as seen through the sight. This action mechanically set the range, informing the sight's ballistic computer how far away the target was and therefore how much bullet drop and flight time to compensate for. With range and wingspan parameters set, the gyroscopes assumed control of deflection calculation. As the pilot maneuvered to track the target, the moving reticle automatically positioned itself ahead of the enemy aircraft by exactly the correct lead angle for the current rate of turn. The pilot simply placed that computed reticle on the target and pressed the trigger. The bullets would arrive precisely where the sight predicted, regardless of the complexity of the maneuvering involved. Production of the K-14 and Mark 18 began in earnest. During spring 1944, the U.S. Army Air Forces received initial priority for European theater operations. P-51 Mustang and P-47 Thunderbolt squadrons began receiving K-14 installations in August 1944. The Navy and Marine Corps followed several months later. F4U Corsair and F6F Hellcats squadrons were scheduled for Mark 18 retrofits through fall and winter 1944. The first Corsair squadrons to receive the Mark 18 were those preparing for carrier operations. Marine Fighting Squadrons, VMF 124 and VMF 213. These squadrons, designated as the first Marine fighter units assigned to fleet carriers, received their gyroscopic sights during training at Naval Air Station Santa Barbara in late 1944. The squadrons would embark aboard USS Essex in December 1944, bringing the Corsair into carrier-based combat operations for the first time. Lieutenant Robert McClurg, flying with the reformed VMF 214, received his Mark 18 equipped Corsair in early 1945. McClurg had scored several confirmed victories during 1944 operations using the standard reflector sight, but he immediately recognized the gyroscopic sight's revolutionary potential. In a letter to his family, later preserved in Marine Corps Historical Division archives, McClurg stated that the Mark 18 represented the difference between skilled estimation and mechanical certainty. The device compressed years of experience into a few hours of familiarization training. Japanese naval aviation intelligence first became aware of American gyroscopic gunsight technology in late 1944 through analysis of recovered Corsair wreckage and examination of captured technical documents. What Japanese technical analysts discovered caused significant concern among tactical planners. Specifications confirmed that American forces had developed a fire control system that largely eliminated human error in deflection shooting calculations. Japanese tacticians understood immediately that this technological advantage could not be effectively countered through improved training or modified tactics alone. The mathematical precision of gyroscopes, spinning thousands of times per minute, could not be matched by human reflexes and mental calculation, regardless of pilot experience level. Japanese fighters had survived against numerically and qualitatively superior American forces, partly by exploiting their superior maneuverability. Japanese pilots could force American pilots into difficult deflection shooting situations where human calculation errors provided some margin of survival. Against Mark 18 equipped Corsairs, that margin vanished. Any American pilot who could track a Japanese fighter long enough to set range parameters would likely score hits regardless of the complexity of evasive maneuvering. Tactical modifications were ordered across all Japanese naval aviation units based on this intelligence assessment. Japanese fighters were instructed to avoid prolonged turning engagements with Corsairs at all costs. The new doctrine emphasized hit-and-run attacks, diving from superior altitude to make a single firing pass before extending away at maximum speed. This tactical shift acknowledged an uncomfortable reality. Japanese pilots could no longer rely on maneuverability alone to survive against technologically superior American gunsights. December 1944 brought a significant operational milestone for Corsair employment. Marine Fighting Squadron VMF 124, commanded by Major William Giese, became the first Marine fighter squadron to operate from a fleet carrier when they embarked aboard USS Essex at Ulithi Atoll. VMF 213 embarked simultaneously, bringing a total of 48 F4U Corsairs to carrier operations. Both squadrons were equipped with Mark 18 gyroscopic gunsights, representing the cutting edge of American aviation technology. The Essex Air Group sorted in January 1945 for strikes against Formosa and the Philippine Islands. Marine Corps pilots flew combat air patrol missions, bomber escort missions, and direct strike missions against Japanese installations, finally bringing the F4U into the carrier-based role for which it had originally been designed. The Mark 18 proved highly effective during these operations. Pilots engaging Japanese interceptors reported substantially improved hit rates compared to their previous experiences with reflector sights. Combat action reports from January and February 1945, now available in National Archives records, document numerous instances where pilots achieved kills with their initial firing burst, a level of first-pass success that had been uncommon with earlier sighting systems. The difference was most apparent during bomber escort missions, where Corsairs maintained formation positions that often prevented ideal attack geometries. The Mark 18's ability to calculate accurate deflection from any angle transformed these constrained engagements into viable attack opportunities rather than tactical disadvantages. Pilots no longer needed to maneuver into perfect 6 o'clock stern positions. They could engage effectively from deflection angles that would have been impractical with reflector sights. February 1945 brought the invasion of Iwo Jima, where Marine Corsairs provided continuous air cover for the assault forces. Multiple Marine squadrons operated from escort carriers, maintaining combat air patrols over the invasion fleet and providing close air support for ground operations. The Mark 18 equipped aircraft demonstrated their effectiveness during defensive missions against Japanese air attacks. Pilots intercepting incoming raids consistently achieved kills at ranges and angles that would have been extremely difficult with older sighting systems. The gyroscopic sight's automatic deflection calculation allowed pilots to engage multiple targets in rapid succession. Where a pilot equipped with a reflector sight might have expended all ammunition on a single difficult target, Mark 18 equipped pilots could achieve hits on 2 or 3 targets during the same engagement, conserving ammunition and multiplying their effective combat power. Squadron commanders noted in operational reports that less experienced pilots were achieving combat effectiveness comparable to veterans, primarily due to the improved fire control provided by the gyroscopic sight. This represented a significant force multiplier for marine aviation, as replacement pilots could be integrated into combat operations more quickly and effectively than had been possible earlier in the war. March 1945 saw the continuation of carrier operations against the Japanese home islands. Marine Fighting Squadron VMF 214 aboard USS Franklin participated in strikes against Japanese airfields and military installations. On March 19, 1945, Franklin was struck by a Japanese bomber while operating off Kyushu. The resulting explosions and fires killed over 700 personnel aboard the carrier, including 32 members of VMF 214. The squadron suffered devastating casualties, but the survivors continued operations after Franklin limped to safety and was withdrawn from combat operations. The disaster highlighted both the inherent dangers of carrier aviation and the determination of the pilots who flew these missions. Despite severe losses, Marine Corsair squadrons continued their assigned missions, providing air cover and strike capability for the fleet throughout the final months of the Pacific War. April 1945 brought Operation Iceberg, the invasion of Okinawa. This campaign witnessed the most intensive kamikaze attacks of the war, with Japanese forces committing thousands of aircraft against the American fleet in desperate attempts to halt the invasion. Marine Corsairs equipped with Mark 18 sights played a crucial role in defending against these attacks. The gyroscopic sight proved particularly effective against kamikaze aircraft, which flew relatively predictable attack profiles that made range estimation and deflection calculation straightforward. Pilots could acquire incoming kamikazes, set range using the sight's ranging reticle, and achieve first burst hits with regularity that would have been impossible with reflector sights. Combat air patrol missions during April through June 1945 resulted in hundreds of Japanese aircraft destroyed. While precise statistics specifically attributing kills to Mark 18 equipped aircraft versus those with reflector sights are not available in declassified records, operational reports consistently noted improved combat effectiveness among squadrons that had received the gyroscopic sights. The psychological impact on Japanese pilots who survived encounters with Mark 18 equipped Corsairs extended beyond simple tactical disadvantage. The experience of being hit regardless of evasive maneuvering, of watching tracer rounds curve through the air with seemingly unnatural accuracy, created a sense of technological helplessness that traditional training had not prepared them for. Post-war interviews with Japanese aviators, conducted by American military historians during the occupation period, revealed that many identified advanced American fire control systems as among the most demoralizing technologies they faced. The certainty of being hit once an American pilot achieved a tracking solution eliminated the hope that had sustained Japanese fighter pilots through increasingly desperate circumstances. Maneuverability could no longer ensure survival. Experience provided no advantage against automated calculation systems, and the only viable escape was to avoid engagement entirely, a tactical impossibility when defending against attacking bombers or protecting their own surface forces. Japanese post-war aviation development reflected these hard-learned lessons. The Japan Self-Defense Force, established in the 1950s, emphasized advanced avionics and weapons systems over aircraft maneuverability. The pilots who had survived combat against Mark 18 equipped Corsairs understood that future aerial warfare would be decided primarily by technology rather than individual skill alone. The Mark 18's technical operation represented a remarkable achievement in mechanical computing. The system operated without any electronics, using purely mechanical linkages, gears, and mirrors to perform calculations that would challenge a trained mathematician. The gyroscopes spun continuously once the sight was powered, maintaining their orientation in space through conservation of angular momentum. As the aircraft maneuvered, the gyroscope housings rotated relative to the stable gyroscope rotors. Precision gears measured this relative motion, translating it into mirror movements that repositioned the aiming reticle. The entire system operated with tolerances measured in thousandths of an inch, manufactured using the most advanced machining techniques available in 1944. Sperry's production facilities represented the pinnacle of American precision manufacturing. Each Mark 18 required dozens of individual components machined to exacting specifications. The gyroscopes themselves were masterpieces of miniaturization, spinning bearings that had to operate smoothly under sustained high-G maneuvering without binding or failing. Quality control procedures tested each site extensively before delivery. Test stands simulated aircraft maneuvering, verifying that the site correctly computed deflection angles across a range of turn rates and target ranges. Sites that failed these tests were returned for adjustment or rebuilding. The manufacturing challenge involved not just producing the sites, but producing them in sufficient quantities to equip thousands of aircraft across multiple theaters. Sperry ramped up production throughout 1944, training workers in the specialized skills required for precision optical and mechanical assembly. Training programs were developed to teach pilots how to use the Mark 18 effectively. The training emphasized understanding what the sight was showing and how to interpret its indications. Pilots learned to recognize when the sight had stabilized after violent maneuvers, when to trust the computed reticle, and how to quickly set range using the diamond-shaped ranging pattern. Ground school instruction covered the basic principles of gyroscopic deflection computation without overwhelming pilots with mathematical theory. The goal was practical proficiency rather than engineering understanding. Pilots needed to know how to operate the sight, not how to design one. Flight training included practice intercepts against target aircraft, allowing pilots to experience how the sight behaved during actual tracking situations. Instructors emphasized the importance of smooth tracking since erratic maneuvering could cause the gyroscopes to momentarily lose accuracy. The Mark 18 worked optimally when the pilot maintained steady pursuit, allowing the gyroscopes to measure consistent turn rates. Training also covered the sight's limitations. The gyroscopes required several seconds to stabilize after violent maneuvers. If a pilot executed a sudden reversal, the sight's reticle would lag briefly before reacquiring accurate deflection information. Experienced pilots learned to anticipate these limitations, timing their attacks to coincide with periods when the sight had achieved stable operation. The statistical record of World War II Corsair operations provides context for understanding the Mark 18's role in Pacific air combat. Marine and Navy Corsair squadrons flew tens of thousands of sorties against Japanese forces from 1943 through 1945. Official U.S. Navy records document that F4U Corsairs achieved an overall kill ratio of 11.1 during World War II, with 2,140 air combat victories against 189 losses to enemy aircraft across 64,051 operational sorties. These figures represent combined results of aircraft equipped with both reflector sights and gyroscopic sights across the entire war. Separating the specific contribution of the Mark 18 from other factors would require access to detailed combat action reports that remain classified or are unavailable in public archives. What can be documented is the consistent testimony of pilots who flew with both sight types. These pilots uniformly reported that the Mark 18 made deflection shooting more reliable and less dependent on natural ability. Anecdotal evidence from squadron records, pilot memoirs, and operational summaries indicates that the gyroscopic sight provided significant practical advantages in combat. This success resulted from multiple factors working in combination. The Corsair's speed advantage over Japanese fighters allowed pilots to control engagement geometry, choosing when to fight and when to disengage. Its rugged construction meant it could absorb battle damage that would have destroyed lighter Japanese aircraft. Its heavy armament delivered overwhelming firepower when bullets connected with targets. The Mark 18 gyroscopic sight amplified these existing advantages by making it easier to deliver the Corsair's firepower accurately. The Corsair itself continued in military service long after World War II ended. Marine squadrons flew F4Us during the Korean War from 1950 to 1953, providing close air support for ground forces and flying interdiction missions. Many of these aircraft retained their Mark 18 gyroscopic sights throughout their operational lives. The technology that seemed revolutionary in 1944 had become standard equipment by 1950, unremarkable and expected. This normalization of technological sophistication characterized the post-war era. Capabilities that would have been considered impossible in 1940 were routine by 1950 and obsolete by 1960. The transformation of aerial gunnery from art to science, accelerated by the Mark 18's introduction, reached its logical conclusion with guided missiles that required no pilot aiming whatsoever. Air-to-air missiles, first deployed operationally in the 1950s, eliminated even the requirement that a pilot maneuver his aircraft to point his weapons at the target. The progression from reflector sights to gyroscopic sights to radar-guided missiles occurred in less than 15 years, a pace of technological change unprecedented in military aviation history. By the time American pilots flew missions over Vietnam in the 1960s, the Mark 18's gyroscopic principles had been incorporated into far more sophisticated fire control computers. These later systems integrated radar ranging, automatic lead computation, ballistic calculation, and target identification into unified packages that bore little resemblance to the mechanical computer of 1944. Yet the fundamental principle remained identical to what the Mark 18 had pioneered. Measure the platform's motion using gyroscopes, calculate the required lead angle, and present that information to the pilot in a form that made accurate shooting possible. The legacy of the Mark 18 extended beyond its direct combat application. The sight's development required unprecedented collaboration between scientists, engineers, and combat pilots. Theoretical physics informed gyroscope design, Manufacturing engineers solved production challenges, and pilot feedback drove iterative improvements. This collaborative approach became a model for future weapons development. The procurement process also established important precedents. Rather than developing entirely new technology from scratch, the United States recognized British innovation and adapted it for American production. This willingness to adopt foreign technology when it offered advantages demonstrated pragmatism that served American military aviation well throughout the Cold War and beyond. The manufacturing techniques developed for Mark 18 production had lasting impact beyond the specific device. Sperry's modular assembly processes, where different facilities could produce interchangeable subcomponents, enabled the massive production volumes that gave American forces their technological edge. Similar techniques were later applied to radar systems, aircraft engines, and eventually electronics, creating an industrial base capable of producing complex precision equipment at scales impossible for other nations to match. The pilots who flew with Mark 18 sights formed a unique generation, transitioning from instinctive gunnery to more systematic technology-assisted combat. Many continued military careers, flying jets in Korea and serving in staff positions where they shaped tactical doctrine around the capabilities that advanced fire control provided. Lieutenant Kenneth Walsh, who had become the first Corsair ace in 1943, using only a reflector sight and natural ability, ended the war with 21 confirmed victories. He received the Medal of Honor for actions on August 15, 1943, when he attacked a superior force of Japanese aircraft despite damage to his own Corsair. Walsh survived the war and remained in the Marine Corps until his retirement, eventually reaching the rank of lieutenant colonel. His career spanned the transition from instinctive aerial combat to technology-assisted engagement, from aircraft armed with machine guns to those carrying guided missiles. Lieutenant Robert McClurg, who flew with the reformed VMF 214 in 1945, survived the war with 7 confirmed victories. He remained in the Marine Corps until 1965, retiring as a colonel. In his retirement writings, McClurg emphasized that while the Mark 18 made deflection shooting more reliable, it never made aerial combat safe or easy. The sight eliminated one variable in the combat equation, but countless others remained: altitude management, energy state, situational awareness, tactical positioning. A pilot with a perfect gunsight could still be outmaneuvered, outclimbed, or simply caught unaware by an enemy he never saw approaching. The story of the Mark 18 concludes not with dramatic endings, but with gradual evolution into more sophisticated systems. As jets replaced propeller-driven fighters in the 1950s, new fire control systems replaced gyroscopic gunsights. The Mark 18 didn't suddenly fail or become worthless. It simply became outdated as faster aircraft and longer engagement ranges required more sophisticated solutions. The Mark 18 Gyroscopic Gunsight deserves historical recognition, not because it was revolutionary or because it single-handedly changed the Pacific War's outcome. It deserves recognition because it exemplifies the less dramatic but ultimately more important work of solving practical problems effectively. In an era that often celebrates breakthrough innovations and disruptive technologies, the Mark 18 reminds us that incremental improvements, when implemented systematically at scale, often prove more valuable than revolutionary changes that cannot be produced or deployed effectively. The device succeeded because it was practical, reliable, and adequately effective. These characteristics, while perhaps unglamorous, define technology that actually makes a difference in operational environments. The Mark 18 story is ultimately a story of people solving problems. Engineers designed it, workers built it, logistics personnel delivered it, maintainers kept it operational, pilots used it effectively, and commanders integrated it into successful operations. The final assessment of the Mark 18's impact must acknowledge both what can be documented and what remains uncertain. Official records confirm that the device was produced in substantial numbers, equipped numerous Corsair and Hellcat squadrons during 1944 and 1945, and received favorable evaluations from pilots who used it. What cannot be precisely quantified from available declassified sources is the exact statistical improvement in kill ratios specifically attributable to the sight versus other factors like pilot experience, tactical improvements, or declining Japanese opposition quality. What remains clear is that the Mark 18 represented a meaningful advance in fire control technology that provided practical advantages to the pilots who used it. It exemplified American industrial capacity, technological innovation, and systematic problem-solving. In an era where aerial combat was transitioning from individual skill to technological systems, the Mark 18 marked an important step toward the automated weapon systems that would define post-war aviation. For the Corsair pilots who flew with the Mark 18 in 1945, the sight was simply an effective tool that made a difficult job somewhat easier. It didn't eliminate danger or guarantee survival, but it improved their chances in combat where margins were thin and outcomes uncertain. The Mark 18 was both an ending and a beginning, the culmination of mechanical fire control and the precursor to electronic systems that would follow. Its legacy lives on in the fire control computers of modern aircraft, sophisticated descendants of the spinning gyroscopes that first taught machines to aim.